Okay, yeah, thank you very much for the for the invitation and for organizing the conference. It has been very nice to learn about all these things. So yeah, so today I will talk about uh, connection between some models of 2D gravity and matrix models, which probably don't have to motivate this conference. So the plan of the talk will be so first I will review some results about Shakib tidal wave gravity, mostly from Schenker and Stanford. Then I will study some generalization that we wrote in a paper with Henry Maxfield from last month, a couple of months ago, and independent work by Witten. And then I will talk about some connections with the minimal string. And this is based on a paper with Thomas Mertens and some work in progress with Mishu Satyuk, a grad student in Berkeley and a grad student in UCSB, Wayne. If I have time, I will talk about applications, but maybe not. Depend. Okay, so first, JT gravity. Um, so this is the action, the theory of dilaton gravity. The first term is topological and is proportional to a constant parameter that you should think of as a constant background of the dilaton. And this will just weight surfaces depending on their topology. The second term is the JT term, which has a linear dilaton potential, so it's phi r plus 2 phi, and the Gibbons-Hawking-York boundary terms. And so we will study this theory in the disk first. So this is the hyperbolic disk, and we have to pick boundary conditions. So we will pick Dirichlet boundary conditions both for the dilaton and the length of the boundary, and they both go to infinity at the same rate in terms of this cutoff parameter epsilon. And this we will call beta the renormalized length and gamma the renormalized dilaton. um, and so it's easy to see from the form of the action that one can integrate out the dilaton, and that imposes the curvature of the surface to be r equals -2. So this is a hyperbolic disk with some um, where I cut some patch consistent with these boundary conditions. And because one can integrate out the dilaton and there is no bulk term, the theory reduces to a boundary mode, which is the Schwarzschild mode, whose action comes from the boundary term. And this was understood in these papers. And this mode can be thought of as a sort of Goldstone mode of the broken conformal symmetry that the ADS2 would have, but is broken by the profile of the dilaton. So if I integrate out the dilaton first, and then sum over hyperbolic surface, which in this case will be just the disk, and reduce to this boundary mode, I can compute the path integral exactly. And this was done in these papers, and I get this answer. So this is maybe more illuminating from the perspective of Stanford and Witten, where you can think of this term as a classical action, this term as a one loop determinant that happens to be exact because of the form of the Schwarzschild action. And this is the topological term. And this beta 2, you can think of this factor of 3 as counting the zero modes of the geometry. And from this formula, you can deduce the density of states in the disk, this formula. And it nicely interpolates between the naive semi-classical answer and large energies, which is this, and this square root h at low energies. Now, if you take this as your theory of quantum gravity, then there is a problem that the spectrum is continuous. In particular, you can compute things like the spectral form factor that decays in time forever, or you can put matter and compute correlators, and they also decay in time forever, and they are related to the fact that the spectrum is continuous. And Schenker and Stanford solved this by including contributions from other topologies. Yeah, so we will consider the case of not only one, but any arbitrary number of boundaries. And we will do the path integral of JT gravity on this space with this some number of boundaries. And in 2D the topologies are simply labeled by the genus. So we will expand in this way, where this term comes from the topological term. Maybe I should have said that this S naught is proportional to phi naught, but okay, this is the topological term. This is the Euler characteristic. And the next step is to compute these coefficients, the contributions for a fixed number of boundaries and handles. And we will still integrate out the dilaton first, but now there is a non-trivial moduli space of hyperbolic surfaces with a given topology and boundary conditions, and one has to take that into account. Okay, so we will sum over topologies of this form, where we imagine any arbitrary topology inside the blob. And the point is that once we integrate out the dilaton and we have a hyperbolic surface, there will always be a geodesic connected to the boundary in these circles. So the way Schatzengger-Stanford figured out to compute these contributions was to separate these contributions that they call the trumpets to the contributions from inside the blob that will be just basically counting hyperbolic surface of some definite topology. And as I mentioned before, the bulk action is zero once you integrate out the dilaton. So this is really just a problem of well, quote unquote counting surfaces. So the ingredients are as I said, the trumpet. So this is labeled by two parameters. The renormalized length the red line is like the holographic boundary, and the length of a geodesic B. And this can be done exactly with similar methods as in the disk, and you get this answer. And this is like the classical term, and this is like a one loop that now has one factor of beta, because the symmetries, the zero modes, you have less zero modes. And then you need to count hyperbolic surfaces with geodesic boundaries. And Schatzengger and Stanford argued that the correct measure in this space to compute the volume is the Weil-Peterson measure. And then the contributions will be the Weil-Peterson volumes. Okay, so the idea is to put all these things together. So we have, in this case, we have three boundaries. So we have three trumpets, and we have a surface with three handles. So this is the contribution from here. And we have the trumpets, and then we integrate over the geodesic boundaries to glue the space. And this gives us the contribution at each genus and number of boundaries. Okay, so after figuring out the systematic way to sum over topologies, they realized that the theory is equivalent to the double scale matrix integral.
Sorry, a clarificational question here. So yes. The original contour of integration of the dilaton is over the half real line or something. So you have to deform this integration contour here?
Yes, you have to deform it, but it's not a half real line, because you should really think of the dilaton as phi naught plus phi as being what you want to call the dilaton. And if you imagine that phi naught is very large, the contour is, if you think of it in the real axis, is roughly from minus infinity to infinity. But
then we should view this as the result up to 1 over phi naught corrections?
No. Yeah, what I was going to say is that when you want to go to finite phi naught, then you should think that you are rotating the contour and integrating over imaginary dilatons.
What's the original contour at finite phi naught?
Well, this is something that, okay, the short answer is, I don't think this is something that people study too much, like how things are modified by
I just want to know if the corrections are order 1 over phi naught or e to the minus phi naught in this claim.
Yeah, so in all these works, people assume that you integrate over the imaginary axis. And I'm not sure what order those corrections are from, but you can define your path integral as saying that you integrate over that contour.
It's a definition?
Yes.
Okay.
At least to give the simplest version of this story.
Okay.
And I don't know, maybe from higher dimensions, it's not that weird that sometimes to get things to be well defined, you have to, like if you integrate over real metrics in general, that's not conversion. Yeah, it just means that it's not that uncommon that you have to define the contours in the
No, it's a problem we confront all the time, but it's not a problem we know a systematic answer to.
Yeah, so that could be something that JT gravity might be useful to study how sensitive it is to those deformations, but I don't think anyone did it. Yeah. Any other question, by the way?
Just one more quick question. In the sum over genus, for the Weil-Petersen volume, is it known at large genus how their volume grows? In the large.
There are some conjectures by Sograf, I think, and you can also. So yeah, it's known.
And it's still well defined. The sum is suppressed at large genus. There's no issue.
No, the series is asymptotic. So the contributions go as like 2G factorial. And then you have non-perturbative effects that maybe from the point of view of the minimal string, maybe you would call them CC branes or things like that.
And from the point of view of JT, is there a way to deal with this asymptotic expansion at large genus, or is this something we also have to complete through an alternative method?
Yeah, I mean, you can think of it as doing some Borel resumation and interpreting the results as you do in the minimal string. But I don't think it's understood exactly what things those non-perturbative doubly or non-perturbative corrections are from a JT perspective.
I see. Okay, thank you.
Yeah, but yeah, I should mention probably later Clifford Johnson will talk more about other ways of doing the sum over genus that might be more useful. For now, I'm giving the simplest version. Okay. Okay, so Sachin and Stanford realized that this theory is a double scale matrix integral, meaning that if I compute this from gravity, the answer is equal to an integral over a matrix H with some probability distribution. And for each boundary, I insert a trace of e to the minus beta H. So this you can think of as an operator that creates a boundary. And the new insight is that the dual to JT gravity is like a thermal partition function where you average over Hamiltonians. And this probability distribution is given in terms of maybe in the matrix you would call the potential of the matrix that has to be chosen to match the disk density of states.
Can I have a quick question?
Yes.
So this quantity on the left-hand side, is this the same as what used to be called macroscopic loop amplitudes, or?
Yeah, it's
the same quantity, but just it's a different interpretation of that quantity, I guess.
Yeah. So that was the new insight, maybe that you should not think of the matrix as some lattice version of the surface, but instead to think of it as in a holographic way, in this way. So we will see the same matrix integral when we look at minimal string, for example, but the interpretation is different. But yeah, the short answer is.
Can I ask you a question about that interpretation?
Yes.
Oh, I'm sorry. So it's a. No, I'm sorry. Never mind. Forget it. I apologize.
No problem. You can ask me later. Okay, just a quick comment, but probably everyone knows it here. So this is, as I said, in a double scaling limit. So first you do an integral over L by L matrices that have a topological expansion in this way. And then you have to do a double scaling limit. Well, in the simplest models, I mean, we want to take a one-cut matrix integral, and then you take a limit where you tune the parameters such that the length of the interval goes to infinity, and the leading density of states looks something like this. And the parameter L gets changed by what we will call e to the s naught. That should be thought of maybe as an average level spacing instead of the real size of a matrix. And the way Sachenga and Stanford show this is to look at the topological recursion. So from the perspective of the matrix integral, one can derive this recursion from so-called loop equations, basically like a Schwinger-Dyson equations for the matrix integral. And in particular, they follow mostly the Einar-Orantin formulation that seems very useful. They found a very systematic way to solve the recursion. And if you give me the density of states in the disk and the double trumpet, basically the case of genus 0 and 2 boundaries, well, this is really universal for, at least in the double scaling limit, for Hermitian matrices. So this is kind of given, you cannot change it. But if you give me this contribution, then the topological recursion gives you all the other contributions for arbitrary genus and number of boundaries. And the idea is that this is a picture from a paper of Einar, is it relates you a contribution with a certain number of boundaries and genus in terms of simpler amplitudes with either less boundaries or smaller genus. Okay, so in summary, so both the matrix integral and JT gravity have the same expansion. And we have these coefficients that we can compute in two different ways. One is with JT gravity in terms of Weil-Peterson volumes, and they satisfy a recursion of their own found by Mirzakhani. And we have another way to compute it, which is in terms of the topological recursion once you give me the density of states in the disk to be this sinh square root E that I mentioned before. And Einar and Orantin proved that the topological recursion for this density of states is exactly the same or closely related in a concrete way to the recursion of the Weil-Peterson volumes found by Mirzakhani. So using this fact, Sachenga and Stanford realized that it's easy to see that both results agree order by order in the genus expansion. And yeah. So this implies that JT gravity is dual to the matrix integral, interpreted, as I said, as an average over Hamiltonian. And like Igor said on Monday, this is closer maybe to the Wigner approach to random matrices than to the previous perspectives. Okay, is there any question so far? Okay, so now I will...
Another quick question. Is V of H known for that row?
Yes, yes, there is a formula that relates V of H to the disk partition function, and you can compute it and it gives you something. It's a little ill-defined, like it oscillates, well, okay, yeah, there is a formula.
Yeah, I had another question. So another completion of this theory you might view as, well, maybe not of the continuum, another UV completion of the continuum, the Schwarzian, is this SYK model.
Yeah.
And that makes the continuum discrete at finite end because the fermions have a discrete spectrum at any finite end.
Definitely.
The spacing, a priori, the spacing from the completion to SYK and the spacing over here are unrelated, but are they similar quantities in terms of their scaling with?
Yeah, because it's not. You should think of in SYK as proportional to n. So that will be the average spacing of the states as well.
So qualitatively, the spacing is similar, but the detailed form will be different.
Yeah. And
can I ask one question? So, in the old story or old perspective, like a double scaling limit was necessary in order to make sure that a continuum worksheet dominates the answer.
Yeah.
But if you interpret it more like ADS-CFT way, then I don't see any a strong reason why we need to take the double scaling limit.
No, that's it. Yeah, that's one of my open questions in the last slide. Why do we need a double scaling limit? And yeah, you can see that you can think of SYK as a matrix integral with a very complicated ensemble. I mean, by matrix, I mean over the Hamiltonian. I mean, of course, it has vectors, but You can think of it that way. And in that case, there is no double scaling limit. But in that case, we don't know what the gravity theory is precisely. We know that it has straight T, but we don't know precisely. So it would be nice to find something in between, right? Where maybe don't need to. Yeah, and that the discussions about, I think the discussions about what happens when you look at one member of the ensemble and things like that are a little bit contaminated by the double scaling limit. It would be nice to have a model like that, definitely.
Double scaling is only needed if you want the endpoint of the eigenvalue distribution to have some higher order power law. The generic power law is always square root from the Wigner-Dyson ensemble. Mm-hmm. So as far as I understand, you only need to do some fine tuning if you want to get to reproduce the exponential part of the density of states. The endpoint is always going to be square root.
You need a fine tuning for, yeah, you need to do a fine tuning to get the whole cinch.
Right.
So you need to fine tune a lot of terms, infinite terms in the potential. Maybe we can talk about that later when I mention the minima string, because maybe that will be in a language more familiar to the previous discussions. Okay, so now we'll talk about the formations of JT. So the motivations are, on one hand, to generalize this duality to more general dilaton gravities, and also an application to 3D gravity that I'm not going to mention because it's probably won't have time. But you can see Henry's talk in strings, where he focuses on that a little bit more. So the idea is to repeat the same procedure, but allow the presence of dynamical defects. And we will sum over any number of them at any position. And this is the formation parameterized by two parameters. One is what I will call the defect fugacity. So every time I insert a defect, it comes with a factor of lambda. And the deficit angle theta that I will parameterize in terms of alpha. So this is a contribution with one defect that will be of order lambda, for example, and this is labeled by alpha. Okay, so when I cut and glue, then these angles, so there is a sharp transition between alpha smaller or bigger than 1/2, for reasons I will say later. But if alpha is smaller than 1/2, or the deficit angle is bigger than pi, there is always a geodesic homologous to the holographic boundary. So we can still use trumpets to glue. So we will glue this, in this case, 3 trumpets, and the Wald-Peterson volume of surfaces, hyperbolic surfaces with cone points. So this is what I call here. So K would be the number of cone points with their angles alpha, and this will be the volume. So the restriction in alpha is important because here is an example with one boundary. Here would be the holographic boundary. So if we have 2 defects, just as an example, with alpha smaller than 1/2, then everything is fine, and we find the geodesic if we draw a hyperbolic surface. But if alpha is bigger than 1/2, or the deficit angle is smaller than pi, then there is no geodesic. This is, well, yeah. This is just a picture to show roughly what happens, but you can see that there is no geodesic. And the Schatzinger-Stanford recipe cannot be applied in this regime. But we will use a different method later to give an answer that is valid in the whole range. Okay, so the ingredients are again all the Wald-Peterson volume and trumpets. And there are 2 new things that we need. One is the disk with 1 defect. This is the partition function. This is the density of states that you would derive from this partition function. It's a cosh. And the second is the Wald-Peterson volume with cone point. And he was explaining in these papers that you can basically, as long as alpha is smaller than 1/2, you can do an analytic continuation and consider a surface with n plus k geodesic boundaries, and then take the k boundary lengths and replace it by 2 pi I alpha. And this changes a hole for a defect, and they prove that this is true. Only for alpha smaller than 1/2. Okay, so this is an example. So, well, this is the exact, or the series that computes the partition function. Now we have a double sum over G, over handles, and over number of defects, where here I allowed several flavors of them with their own angles. and each of them is computed by gluing trumpets. And so, for example, here we will have a sum, if we computed the one boundary partition function, a sum over genus, so this is genus 0, and for each genus we have a sum over defects, with this would be like no defects, one defect, two, etc. So the main question we would like to ask is, can we perform the sum over defects explicitly to get the new density of states? And more importantly, yeah.
Could you go back to the previous slide? I'm confused about something.
Yes.
In the top formula, where is the dependence on alpha on the left-hand side?
Oh, I didn't write it. Sorry. Yeah, but the answer depends on alpha. Yeah.
But how many are there?
No, you can choose which ones you have. So it's for now we are putting them by hand. It could be just one, but so to define the theory, we decide how many flavors of defect you have, and you have to tell me their alphas and their lambdas.
So you're saying there's a different left-hand side for each set of alpha 1 through alpha k.
Yeah. So you should think of it as a 2-parameter or 2 times the number of flavor defects parameter deformation of JT gravity. So this will depend on it, of course. I will mention later one reason why would you want to study this, but for now it's a definition.
But should I think that those alphas are like somehow fixed by some more microscopic considerations? That like they have to be.
Yeah, for example, if you study 3D gravity, you will see that the alphas are related to the parameters of SL2C transformations. Well, they are fixed, for example. But from the 2D perspective, it's a choice. But
I see. So those are like, I should think of those as different UV completions of JT gravity.
They are not. I would say that they are different from the point of view of 2D theories. They are just different theories with this 2-parameter space of different theories.
But some of them may not have consistent microscopic realization, I guess.
No, but most of them, we will see that most of them have a UV completion, which is the matrix integral. Yeah. Okay, so that's the question here. Is the theory dual to a matrix integral? And we see that the answer is yes. With the only difference being that you have a 2-parameter deformation of the matrix potential. Okay, but sorry. Before it's instructive to ask the following question. So we define the theory by summing over defects, but why did we have to do that? Can we define it where we say we have only one or any finite number of defects, for example? And the answer is no, and it's important to sum over the number of them. And this is analogous to, so the case if we would fix one defect, for example, would be analogous to the Maloney-Witten partition function in 3D, and it's ill-defined for similar reasons. So for example, so this is the density of states at very low energies. So this is the disk, and it's I'm looking at where the approximation is the square root h. If I add one defect, then you'll get this term. And this blows up at small energies. If you want it to be, it's not going to be related to a matrix integral for sure, etc. And if lambda is negative, at some point rho will become negative. So this is definitely problematic. And when you sum over defects, so you get terms for 2 defects, 3, etc., terms that are more and more singular in the energy. And the reason is that once you resum them, that we will do soon, this resums into a square root h, but shifted by a 0-point energy proportional to the fugacity. And this was done at low energies and perturbative in the fugacity, but this is true at finite lambda as well. So to compute the density of states, we need to know something about the Weil-Peterson volumes, and we derived the formula for the Weil-Peterson volumes at genus 0 and n boundaries in a paper with Thomas Mertens. And well, we did it using the minima string, so it's like a physicist derivation. And so this is the formula. So this is some function of the lengths and u of x, and u of x is defined implicitly through this formula. And for those of you that knows about it, this is basically the string equation of JT gravity. And a similar string equation was found by Sograph as a generating function of volumes when the b's are equal to 0 in the 90s. And okay, and the idea is to replace the borders by defects with this replacement. And I should say that this formula was also derived from first principles recently by Timothy Budd. Okay, so after I sum over all defects, I get this formula for the density of states. This looks complicated, but okay. I mean, it's a formula. We then realize it simplifies considerably if you put E naught to 0. Then you only have this linear correction, and in general, E naught is given by this formula. So this you should recognize, or you should think of it as a string equation. If you replace E naught by U, as the string equation of JT gravity with defects. And you can check that this matches with the perturbative calculations. So here's an example of doing that integral numerically. So for negative fugacities, you get everything is fine, and you see instead of blowing up, the spectrum just ends abruptly at some positive energy. Here the dashed lines is the Schwarzschild and the JT, and black line is the defect. When the fugacity is positive, then nothing happens until you reach a critical value where the density of states starts becoming negative. So okay, this is just so at this point, yes, sir. Is there a question?
Did these corrections change the large energy asymptotics?
No, as if you look at this formula, no, as long as alpha is smaller than 1. But actually, we're doing alpha smaller than 1/2, so even more no. So this grows lower than this. So roughly, the JT grows as e to the square root e, and this correction grows as e to the alpha square root t, but alpha is smaller than 1.
Okay, thank you.
Yeah, so all the curves eventually go to JT at high energies. But okay, so this is some interesting feature that we don't understand very well, and it seems like the theory is only defined below some critical fugacity. And interpretation and fate of this is an open, I guess it's an open question.
Does the critical fugacity depend on the choice of alphas?
Yes, but it's always like order 1. It depends a little bit, but it's always some order 1 number.
Mm-hmm.
Yeah, it doesn't go to 0 or infinity, some fixed number. It slightly depends on alpha.
Does it depend on how many different species there are? Like if you take the limit.
Yeah, we didn't look at that case with several species, but I would say probably yes. So this was just done with one species.
Thanks.
Yeah. Okay, so an example that is easier to work out. So we want to see that the theory is dual to a matrix integral, and it's easier to. A nice case to look at is the double trumpet that is supposed to be universal. So this is the universal answer for a double-scaled Hermitian matrix integral with an arbitrary position of the edge of the spectrum. And the gravitational answer, sum over defects, gives precisely this to all orders in lambda. So this is the first check that this is, or the second check that it might be dual to a matrix integral. And let me mention briefly how the calculation goes. So that these two boundary partition function, you have to sum over defects, this is k. And for each number of defects, you integrate the trumpets and the Weil-Peterson volume. When you plug these formulas that we derived with Thomas, you get this, where this comes from integrating over B1 and B2, and this comes from the Bessel functions that appear. It happens to be that there is a nice result that allows us to do this sum that is basically made for this type of sums, which tells you that for any arbitrary function g of x, f of x, and parameter y, if you do this sum, the answer is precisely the same function g, but evaluated at a different point. And here you can see that this f, sorry, maybe I should have used k here, but okay. Y is like lambda, x is x, f is this Bessel function, g is this exponential, and we will find that the answer is basically this, evaluated at a different point. So after using this, we get precisely this formula, and this u of x that we define is given by this. So now you can see clearly that this should be interpreted as the string equation of the model. And you can actually do this for any number of boundaries, and you get this formula. Even for the case of one boundary, you can interpret this -1 as an integral, and you'll get the same as before with the string equation. And this is precisely, so I didn't use any matrix model input yet, but this answer is precisely the same as the correlators of a Hermitian matrix integral computed in these references in the 80s. So this is not, it's only universal for n equals 2, but in general it's given simply in terms of this function u of x. Okay.
So can I ask a question? At critical value of lambda, there is a point in which like a density of state touches 0, right?
Yeah.
Is there anything interesting if I zoom in that region?
Not that I know. Yeah. Yeah, I don't know. Yeah, I would like to know what happens in that case. Yeah. Yeah, it goes linearly. I mean, it doesn't go as a square root edge or anything like that. Yeah.
So,
yeah.
So there's a region. So going back to the original sort of, understanding of JT gravity from Stanford Witten, there's sort of there's an edge region. The square root of the density of states is sort of dominated by large fluctuations in the JT gravity path integral. And then the region where it grows exponentially is basically the black hole spectrum. Mm-hmm. So are these modifications only affecting sort of the region near the endpoint where things are dominated by large quantum fluctuations, or is it also reaching into the black hole region where sort of classical JT gravity is important?
Yes, I mean, it modifies the density of states everywhere, but as you go to higher and higher energies, it becomes small. Yeah. So I don't know if maybe by what you mean, then I would say that it doesn't affect the. I wouldn't say that it's black hole region, but the semi-classical black hole region. Yes.
Semi-classical black hole. Yeah. So this is all sort of affecting the region in which quantum gravity corrections are important.
Yeah.
Okay.
Yeah. Okay. So we gave a lot of evidence, and now there is a result from Einar and Orantin that actually tells you that the model is dual to a matrix integral, and this is called the deformation theorem. And what they do is to show that if you give me a solution of the topological recursion given by WGN, and here W is the result. I mean, this is the correlator of the resolvance, not the e to the minus beta h. Then you can generate a new solution of a topological recursion in this way. And this depends on the deformation parameter lambda, that of course will become the fugacity of the defects, a contour gamma, and a function f. And this solves the topological recursion. And what we show in the paper with Henry is that for a certain choice of gamma and f, this is precisely the sum over defects. So maybe I would say we didn't show that it's a matrix integral, we just show that it satisfies the topological recursion, or Einar and Orantin show. And this result is important in some applications to show the integrability of the recursion, but okay, it's not going to be important for us. So to summarize, we have the same topological expansion, whether we think of a matrix integral or a JT gravity. We can compute it from gravity as a sum over the meters on volumes, including defects, and from the matrix integral in terms of applying the topological recursion to the new disk plus defects density of states. And this result of n guarantees that both procedures agree. So this implies that this deformation of JT gravity with the gas of defects is dual to a matrix integral, or at least it satisfies the topological recursion and is dual whenever the density of states is well behaved. And again, interpreted as an average over Hamiltonian. So one motivation to study these deformations is the connection to dilaton gravity. And the idea is that, so we saw in this paper with Thomas from last year and also explained in more detail in the paper of Witten, that you can think of inserting a defect and as inserting this operator in the matrix integral, in the dilaton gravity, in the JT gravity path integral. And basically, this is proportional to 5 times r plus 2. So when you add this 5 here, it will modify r plus 2 equals 0 to r plus 2 equals some delta functions where the insertions are. And that's precisely the defects. So when you sum over any number of defects, then you get this formula, and this just simply exponentiates. So basically what you have is that you should add this term to the JT gravity action. So then the JT gravity with the gas of defects is equivalent to the following modification, where I have this generic dilaton potential, which is the JT one, plus this exponential terms in the dilaton. And I put this double dot just to indicate that you need to pick some prescription to define those, each contribution from like contact terms of the dilaton, etc. So, but okay. And so going back to the question that was asked before, so picking your spectrum, let's say, of defects, is just like picking your dilaton potential. And this covers the last class of two derivative dilaton gravities, since this is the most general form. And I say large class because alphas are restricted in the range. Okay, is there any question about this? I will change topics now.
Yeah, I have another question. So your statement that you're forced to sum over the defects, I guess that's like saying that it's a like normalizable excitation that you can't impose that it's there from the outside. Is that true for all values of alpha?
Yes, because so if you look at the formula, yeah, the idea is that the square root, not the square root, the correction at low energies near the edge is independent of alpha here, and yeah, this will blow up, right? I mean, even if lambda is positive, this is bad.
Okay.
Especially if you want to compare to the matrix integral. So, and if lambda is negative, even worse.
Yeah, I see. Thanks.
Or any alpha. Yeah. Okay. Any other question?
Yeah. I have a question. So how large is this? Is it any? Can you, in terms of functional space, if I pick, well, I have a very particular potential in mind, but what are the restrictions on this class of potentials? So you would say it's any potential that can be written as phi plus the sum?
Yeah. Here, I mean, I think there is
but
no
this
problem.
isn't a Fourier, and alpha is real. So what's the condition on alpha? It's restricted?
Yeah, alpha is between 0 and 1/2, or actually I will show now how to do it from 0 to 1, but let's say alpha is 0 to 1, and lambda has to have certain constraints if you want the theory to be well defined.
So this doesn't include functions that have meromorphic functions of phi, or does it? Do you know what kind of analytic structure is allowed by this class of functions in the complexified phi plane?
I mean, I really didn't think about it too much. If you ask me, I would say what I told you, like this range on alpha and this restriction on the sign of lambda. Well, not the sign, but yeah, no, but that would be interesting to understand better, to see which problems this can be applied to. Yeah.
Seems this is also related to the question that was being asked earlier about what do you do for a large negative phi?
Yes. Yeah, I don't know. I mean, yes, I would like to know how sensitive all this is to different contours, but I mean, I really don't know.
Well, the point is that all of these terms blow up, but if alpha is between 0 and 1, they all blow up at large negative phi, right?
Yeah.
So this is a very particular class of functions here.
Yeah, there are potentials that go down and then up. Sorry. Or what? Depending on the sign, they look very different depending on the sign of lambda. Yeah. Sorry, is there a question? Yeah.
A question, yes, sorry. Can you, so alpha should be, in which interval alpha are allowed? From 1/2 to 1?
From 0 to 1/2.
From 0 to 1/2. So you cannot make out of this potential, for example, a Gaussian potential in phi. Or you can?
A Gaussian?
Yeah, suppose you tune lambda i's and alpha i's so that you have phi plus phi square with some constants. Can you do it, or it's why?
You mean take alpha to 1?
Yeah, just to make what we called in the old times R square gravity, because if you integrate out phi, you would have R plus R square with some coupling.
Yeah, I will comment on that later.
It's interesting because we solved it long ago by other methods. We have the answer.
I know.
This model.
Yeah, I know.
Mm-hmm.
So I will mention the solution when alpha is close to 1, and we will see that it's completely different. And but yeah, it would be nice to connect to your method. But,
yeah, it would be nice if you can use the Gaussian potential for phi.
Yeah.
Mm-hmm.
But okay, we will see that the formula becomes much complicated when alpha is close to 1.
Mm-hmm.
But okay. So maybe let's, unless there is a question. Okay, so now I will talk about the connection between all this and the minimal string that might be more familiar to some of you. So as you all know, and some of you invented, the minimal string is this combination of a minimal model, P, Q, with Liouville and ghosts that satisfies the central charge is 0. And we will focus on the 2, P series that is known to be dual to a 1 matrix model. And the Liouville coupling is this. So it was noticed already by Sachenker and Stanford that when you take P to infinity, the theory becomes JT gravity, or at least they show that the density of states is the JT gravity one. And the new twist again is to interpret the matrix as a random Hamiltonian. Just to mention briefly about this check. This is
sorry. These are unitary or non-unitary minimal models?
Yeah, these are the non-unitary. Yeah.
I see.
So this central charge is going to minus infinity when P goes to infinity, and the Liouville mode is going to plus infinity. Yeah. Okay, so this is a quick. This calculation was done a long time ago, but we want to compute the disk partition function at fixed length.
I'm sorry, can I interrupt again? So is there a way actually to map JT gravity into Liouville theory?
Yeah, I will mention it. Yeah, that was done. Okay, I will mention it in a couple of slides. Yeah.
Okay.
I suspect what's going on here is that in the JT gravity action, the phi field is null, and the Liouville field is also null, right? It's phi r. So it's sort of like a null kinetic term for the conformal mode of the metric. Whereas in the minimal model, the Liouville field is space-like, and if I want to think of the matter field as being, generated by some sort of Feigen-Fuchs prescription, the Feigen-Fuchs field has a negative kinetic term. But so by taking C goes to infinity, I suspect what you're doing is you're making the Liouville field, you're sort of taking some kind of light-like limit
Yeah, yeah. I think I will phrase it in a different way, but I think it's precisely what you're saying. Yeah.
Okay.
I see. From the SYK point of view, I mean, there's this paper by Mandal, Nayak, and Warrior. Maybe Spenta can say a bit more about that, where the claim was that the SYK low energy sector is actually dual to Polyakov action. Is there a connection here, rather than JT gravity?
Yeah, I know about that paper, but I think about it. I didn't think about it in this context. Maybe we can ask.
Maybe
Spenta.
Spenta knows.
Yeah, well, I mean, okay, I mean, is this a good time to make a comment, or maybe?
It's a perfect time to make a comment.
Yeah.
Okay, thank you. So if you think about the SYK model as around the infrared fixed point, there is an infinite dimensional group, the Virasoro group, that characterizes that fixed point, and what we considered was the coadjoint orbit of that Lie algebra. And then there is this old work of Alexeyev and Saakashvili, actually, which very beautifully showed that this coadjoint orbit describes a theory of gravity, a Polyakov theory of gravity. And of course, there are some other assumptions we had to make regarding the cosmological constant, etc. But then this reduces to a Liouville type of model for the conformal mode. And if you look at the low energy, if you look at the degrees of freedom of this Liouville theory, plus some constraints which are important that come from the gravity theory, then you get the Schwarzschild action exactly the same way you get it for JT gravity. So JT gravity and this Liouville type of theory, they reduce to the same model, which is the SYK model. This is the thing I'd like to say. So this is a precise statement, actually, what I just made.
Spenta, can I ask
I don't know exactly how to map the Liouville theory into the JT gravity. It's just these boundary degrees of freedom, which is all that is in the JT theory and in this Liouville theory, are identical.
Spenta, can I ask something? So these constraints, they remove the dynamics of the Liouville mode or of the conformal mode, right? And they keep only these boundary fluctuations only, or?
Yes, these constraints basically get rid of the conformal degree of freedom, and only the large gauge transformations then remain to be the degrees of freedom. Yes, that's true. So it's not only Liouville theory that there are T plus plus equal to 0 and T minus minus equal to 0. Two constraints are there. And okay, thanks for that comment, Panos.
Was there any matter coupled to gravity required there?
No.
No, okay.
No, this was just dilaton and the metric of JT. No matter was coupled. At least not in our discussion.
Okay.
All right.
Okay, thank you. Yeah, thank you for the explanation. Yeah, I didn't think about the connection with that paper. I could take a look. But it sounds like it's probably related. Yeah, so what else? Okay, yeah, so this is a quick slide to show how to compute the disk partition function. We want to do it at finite for boundary conditions of fixed length. So this has been studied over and over, in particular from the Liouville perspective by FCC and T. And so the idea is to compute first the partition function in the disk with fixed boundary cosmological constant, which I parameterize in terms of S this way. Kappa is related to the bulk cosmological constant. And and then to get the fixed length, I do a Laplace transform, inverse Laplace transform. And the idea is to, in the mu v plane, you can rotate the contour, and the integrand always has some branch cut in the negative real axis, and when you rotate it, you are basically computing the discontinuity of the FCCT answer along this line. And then you get the final answer to be this, which if you do the integral, you get some Bessel function that might be more familiar from the old literature. But this is the density of states. And so for example, here, this term comes from the changing variable from mu b to s. And this term comes from the discontinuity of the FCCT answer. This is the discontinuity in mu b, so that's a little hidden through the mapping from S to mu b. And from here you can read off, so the boundary cosmological constant is roughly like the energy conjugated to L, which is the boundary length, and this is like the density of states. Okay, I will skip this, but I will describe things in terms of the string equation instead of the density of states, because it will be a little bit, we found it to be a more compact way of describing the models than to give the density of states. But there's a one-to-one map between the string equation giving u of x and the disk density of states. For example, they are related in this way. And this comes from the free fermion picture derived from the method of orthogonal polynomials, and it's a completely different way to the topological recursion to compute corrections. Heterogeneous that we probably will listen to by Clifford Johnson after this session. But okay, so the density of states of the minimal string is this, where I rescale energies in a convenient way. And if you take large P, you get this, the JT gravity answer. And in terms of the string equation, the minimal string equation is this hypergeometric function that is actually a difference of Legendre polynomials that goes to the JT gravity string equation. And this is maybe related to what I think Emil was saying, that you need to tune. So in the usual multi-critical model, you will tune only like 1 power of u, but to match to the continuum and to match to JT, you need to turn on a lot of terms that, well, should be thought of as a analytic redefinition of coupling constant. And here I mentioned some papers where people use these older ideas applied to JT gravity or JT gravity like models. So yeah, here I was going to mention an argument of why this works. So this was done by Seiberg and Stanford, and also this other paper that did the same derivation without calling it the minimal string, but did the same. And the idea is that you describe the minimal model as a time-like Liouville. This is, at least for me, an open problem, like how accurate this description is. So that's, maybe you should see this as a motivation. And the Liouville field. And if you do a field redefinition from phi to chi to rho and big phi, and now in the minimal string, phi is interpreted as the scale factor of the physical metric. And now if you define rho and interpret rho as the scale factor of the physical metric, so you redefine the metric and the time-like Liouville, then you get this action here. Where the metric here, I just wanted to stress that this metric is not the same as the physical metric of the minimal string. And when you take large P, this goes to the linear JT answer. And this is related to what Emil was saying as well. And this might be related to Spenta's paper as well, but I didn't think of it. And so this you should think of, so two things, at least in my mind, that I would like to understand better are, why is this a good description of the minimal model, like in more detail? And also the boundary conditions, because here you would say, okay, I take P to infinity, but if I look very, very close to the boundary of ADS2, then phi is blowing up. And then you could say that you have JT in a finite region in the bulk, but then if you go to the UV very near the boundary, then the theory is modified and the minimal string effects are important. So it's not completely obvious that this is a rigorous derivation, but at least roughly take as a motivation. Okay, so the question I wanted to answer, if I have another 5 minutes, was so we know that JT gravity with defects has these string equations, and then we can ask what is the minima string ancestor that at large P gives the defects, right? And the answer, okay, I will skip this. The answer is very reasonable, and that's what we are working on now. The answer is, let's see what happens if you deform the minima string action by a natural operator, which is a gravitationally dressed primary operator of the minimal model. Then the string equation was derived, or at least conjectured, with a lot of, it's almost derived by Belavin and Samolochikov, building on previous work of Moore, Cyber, and Staudacher. And one gets the undeformed minimal string, and this is perturbed by these terms where this tau is related to the coupling, and these are Legendre polynomials that depend on n, where n is the label of the primary operator. And there are some higher order terms that I'm not going to write down. And if you take the large P limit of this formula, you get precisely the string equation of JT gravity with defects. So in a sense, JT gravity with defects is the large P limit of the deformed minimal string. And if you do the same trick of field redefinitions, you get that this is the action.
So I have a question.
Yeah.
Going back to, so these are non-unitary CFTs.
Yeah.
Coupled to gravity. Is there any remnant of the negative norm states from the perspective of JT plus defects? Are those related to this negative density of state you find? It's strange to me that you don't have any indication of the negative norm states. Or are all those gauged away by the Virasoro constraints?
I think not. I think if I remember from the older literature, if you compute the sphere partition function, forget about JT gravity. If you compute the sphere partition function and you expand in genus, I think there are some terms that are supposed to be positive, and if you do the minima string with 2, P, they can become negative.
Well, but here we're doing it on a disk.
Yeah.
I want to know in the JT picture if there's any remnant of the non-unitarity of the minimal model.
Okay, I'm not sure. Yeah, maybe we can discuss it later. But yeah, I don't know. The density of states is positive. Yeah, I'm not sure. I mean, you have the problem that I mentioned of the negative density of states, but that's just a problem when you turn on these couplings and make them too large. But I guess your question is even without the deformation.
Well, I don't know. It's just strange. Usually if we couple a non-unitary matter to gravity, the non-unitarity manifests itself somewhere. Of course, here we have so many constraints to diffeomorphisms that maybe
of course,
it kills all the non-unitarity, but this seems to be something to. Do people from the older days know the answer to this question, perhaps? Okay.
Not off the top of my head.
What? Once again, can you formulate the question?
The question is, he's relating JT gravity to a non-unitary string coupled to 2D gravity.
Mm-hmm.
The non-unitary string on its own has negative norm states.
Mm-hmm.
I wanted to know whether these manifest themselves somehow from the JT gravity picture.
I also wouldn't say.
Well, if this is the large P limit, this means that the JT gravity is somehow imitated by Liouville gravity with matter charge, central charge going to -infinity. Yes.
Yeah.
And this is there is a non-unitary theory, which is the loop gas model. For or ON model with n equal to -2. So here you have positive and negative weights of in the partition function, and this explains the fact that the theory is not unitary.
Mm-hmm.
These are models that you studied and also with Staudacher?
Yes, yes.
Thank you.
You mean in the sphere partition function? Or can you
yes.
see it in? Yeah.
But you can
So
generalize to any genes.
Which models do you mean, Ivan?
N equal to -2.
Ah, of course, yes.
The dense phase.
The trees.
Yeah, I think what may happen is that the 2-point functions of these O1 comma n operators are actually negative, right? I don't remember if this actually happens, but it may happen in these non-unitary series.
Right. The question is whether the gravitationally dressed analogs of these things survive as observables in JT gravity, because JT gravity somehow has no observables in it. So either these operators have been truncated somehow, or I don't quite understand what's going on.
I thought those were the conical defects that were being added.
Yeah, those are the conical defects.
So do they have negative 2-point functions or anything like that?
They might, certainly. I think there is no, often this is what happens in non-unitary series.
But I thought Joaquin told us we shouldn't take those seriously on their own.
Well, the question is, what's the sign of the lambda squared term, right? Like when you perturb by, maybe it affects the sign of this term. Yeah,
I mean, I see that from the CFT, worksheet CFT, but I'm confused because if you give me, I don't know how to see it if you give me the string equation, where is a problem or not. And maybe you didn't tell me where it came from, and then I don't know what, well, there are problems if I compute the sphere partition function, like we were saying before, but yeah.
A quick comment.
Yes. Yeah.
I don't have a complete answer to this question, but I suspect that there's some signature of what in any given minimal model would be interpreted as non-unitarity. I suspect there's some signature if you ask the right things in JT gravity, but I think the things we've been caring about so far just don't care about those things. And that's somewhat evasive answer, but I think it's sort of, and I'll try and comment on this when I make some comments in the discussion session, but I think we're still learning a lot of this business of, if you like, repackaging a number of the various elements that were more upfront when you're considering these models as string theories, and these are string worldsheets, and there's some space-time additional to that, versus those worldsheets actually being the gravity itself. And I think that changes what observables are and what the right questions to ask are. And I think these issues are probably going to be resolved by essentially figuring out what the physical observables are from this being a gravity question. So, for example, I don't think it shows up in the partition function, the spectral density, as you've just demonstrated. But that's not a complete answer. I just wanted to make that comment.
So what's the interpretation of surfaces that don't have a trumpet on them? From the JT gravity point of view.
Oh, just what's the present? Where is the presence of?
So, for instance, if I looked at, so people were speculating that there's a problem with the positivity of the sphere 2-point function.
Yes.
Or maybe some issues with the torus partition function having negative weights in it.
Right. And so the question is, do those things show up on their own without trumpets attached?
Right.
In the story somehow? Kind of. I don't have a good sentence. Let me see if I can formulate a better answer to that. I don't know if you're going to be around in the discussion section.
Yeah, I'll be there.
I'll try. I might not have a sharp answer. I have an intuitive understanding of where it all is, but I'm still sort of coming up with all the words. So I apologize. Off the top of my head, I can't It's okay. Let me try and say it. What happens? And sorry, Joaquin, we're sort of taking over your your last 5 minutes, but you know, it's partly because all of those things you're just talking about, they show up explicitly in the thing that Joaquin's calling U there, that function U, and ultimately that device, from the string theory perspective, would be the thing that, you know, we integrate up twice and then interpret all the terms as the genus expansion in the free energy of the string model. Right. Here it sort of, and so there you would see things like the sphere and the torus, et cetera, et cetera. In this language, what we use this sort of differently, right? This ends up being the potential of this associated problem, for which we then look at the wave functions. And in some ways, it's the wave functions in this potential that become the building blocks of the JT gravity, at least from the perspective that I like to think. So in some ways, all of these things that we look at for interpreting the space-time string properties, which are the terms in U, they just become this auxiliary potential that we work with in the JT gravity. So it just sort of, a lot of the physics is interpreted differently. And I don't have the full answer, but all of those things, like the various surfaces without trumpets are living in it as defining this potential, which we then build wave functions for and construct the loop equations for. So I've probably just confused everybody with that remark, but that's where it lives, and I don't have a good, okay. I'm writing something now that might expand on this a little bit, but I think the key that connects these things nicely are actually the FCZT branes. And in some sense, what happens is that you see, if you think of those as probes, those, you can have strings stretching from those to the various surfaces with holes drilled in them. And those are sort of the connective tissue between the JT language and the old string language. Okay, I'll stop free associating now.
Can I make a quick comment? Sorry, Emma, I thought the answer to the question about disconnected surfaces was that there's some like exponentiation of the disconnected diagrams, which just produces a constant prefactor to all of these quantities, to the things that do have boundaries, to the, you know.
That may also be true. I'd have to think about. Yeah.
Yeah, in JT gravity, we usually think of the matrix integral normalized by that. So it cancels. If you it's like a normalization of the distribution. No?
Let me not hijack your session anymore. I'll be in the discussion session. If someone wants to bring this up again, I can point explicitly to the different pieces of the formalism, and we can really unpack that if you wish. Maybe this isn't the right point, but I suspect that's kind of true as well. But I don't think they're completely invisible. I think they're a crucial part of the story.
I mean, if you think of these lambdas as being couplings to observables, then there are contributions to even the single trumpet, where you have a disconnect diagram where some of the conical defects are attached to. So yeah, it doesn't like disappear entirely into the normalization.
Yeah. Probably that might be related to, let me see, if you look at, where do I have it? Maybe related to what Igor was saying, that this negative sign here, roughly, I mean, that maybe the things that come square that should be positive have negative sign. But well, if you compute the whole density of states, is positive. So I don't know.
So, Boloria had his hand raised. I don't know if it's from before or is it from now.
No. My question is about precisely this formula, which is in the next to the last line. It seems that the potential is completely unstable here. Yes, sinh. So you should already understand it like Airy function in some sense of deformation of the contour of integration, yes? So does it mean that is it the sign that we are dealing with non-unitary models?
That could be also, but I mean, I want to say that this derivation of this potential is like is not at least maybe Douglas or someone else knows. For me, this is just a motivation of why these matches work, but because of this subtlety with the minimal model and the boundary condition. But it's true that if you take this too seriously, it might be problematic as well. But
you still cannot tell me whether you can cook up from this R square gravity, like with the action R plus R square.
Yeah, so okay, I have like 2 more slides and that's it.
Okay.
Sorry. Yeah, no, that's fine.
all right, go on.
Yeah, I'm almost there anyway, but okay, so.
Sorry, can I ask one question? So here you're saying that alpha can be anywhere from 0 to 1.
Yeah, that's the last 2 slides.
Okay.
Yeah. Okay. Yeah, so okay, here I draw alpha and alpha 1 corresponds to the identity and alpha 0 to the n being roughly p over 2. Yeah, so what happens, how do you see a barrier at 1/2 here? When alpha is between 0 and 1/2, then these higher order terms are 0. They are not there, even in the minima string. And this is because this comes from analytic redefinitions of the coupling, and only couplings that obey some resonance condition can mix. And if alpha is between 0 and 1/2, then it can only appear linearly. And this is explained in the Belavin Samolchikov paper. But that's a nice thing about this, is that this solution doesn't care about the range of alpha, and you just have to include the higher order terms. And okay, this is the answer. This is the string equation for a gas of defects with arbitrary alpha. I don't know how to compute it from JT since there are no trumpets. It's very non-analytic in the angle as opposed to things we maybe wrote in the paper with Henry. And yeah, so what Kazakov was saying, I think you should take alpha to 1 of this formula, and that seems a little complicated. So I don't know how to do it, but maybe one can look at it. And so this formula is derived from the minima string, and we will conjecture that is the correct answer for JT gravity. One little check, you can send alpha to 1, and then it will be a gas of no defects. So you should recover JT. And when you send alpha to 1, these sums become infinite. And this simplifies. And when you do this sum explicitly, you get back the JT gravity string equation up to some shift of the ground state direction. Okay, well, one more comment, you can compute boundary correlators, and these are, I'm not sure what they mean in the JT gravity perspective, because they're like boundary versions of these guys. But if we are saying that we are putting Dirichlet on the metric and the dilaton, I'm not sure why they are not trivial, but if you compute them in the worksheet CFT perspective, they have very complicated answers, and actually in large P they become the JT gravity correlators, and we don't understand very well why. So this was in the paper with Thomas from last month. But if one comment here, when you compute these boundary correlators, you will see that their dimensions, if you put the spectrum of the minima string. So this is equation for Liouville, but you can apply it to the minima string. The operators will have negative weight, of course. So the 2-point functions will behave as, if you interpret this length as a boundary Euclidean time, you would say that these are very non-unitary. So this is one way in which the non-unitary shows up. If you look at the formations in the boundary, like looking at the disk boundary correlators. Okay, so that's all. Okay, maybe I should finish because it's kind of late, but okay, this is just a list of open questions I would like to understand, how to extend it to theories with matter. Maybe we can do some mix between the minima string and C=1, where we put the minima string to generate something that looks like JT gravity and then add some C=1 field or something like that. This, for me, important question, how to go away from double scaling. Can we do finite cutoff ADS, and what is the matrix interpretation? So this is probably the paper that was mentioned before. So can we understand this matrix model as arising from triangulations of surfaces of constant curvature? Another comment, the boundary correlators that we got for the minima string look very similar, although they are not the same, to the correlators of double scale SYK. So it would be nice to understand this better. Okay, we can do the sitter. DS2, there is a similar matrix model with that we studied in a paper with Malacena and Yang, and these other references are relevant. And finally, there is some, if you look at near extremal states in higher dimension, there is a sense in which JT gravity should be universal in some limits, maybe not the non-perturbative corrections, but just the disk. For example, we studied this in the context of CFT2 in this paper, that if you look under very general assumptions, there are CFT2s that have the Schwarzschild sector hidden there. And I think that would be nice to understand as well, the more applications to higher dimensions. But okay, that's it. Thank you for your attention.
Okay, let's thank Joaquin for a nice talk. And now let's move it to some questions. I see Panos.